So in two dimensions, given a single vector, it's pretty easy to find all of the vectors that are perpendicular to it. Assuming that it's non-zero, all you have to do is swap the coordinates, make one of them negative, and there you go. You've got a single vector which is perpendicular to the given one, and then you can obtain every other vector by taking scalar multiples of that one perpendicular guy. And that's pretty much something that you probably have seen sometime in your life, where you learn that the slope of a line perpendicular to a given line is the negative reciprocal. That's pretty much it. In three dimensions, it's a little bit different. It's more complex. First of all, given one non-zero vector, you don't have just a line of perpendicular vectors, you actually have a whole plane of perpendicular vectors. Second, if you have two vectors, in general, they're going to actually form a plane. Unless they are unless they're parallel to each other, they will form a plane. And if they form a plane, then there will be a unique line of vectors that is perpendicular to that plane. So a common question will be, given two vectors A and B, can we find a vector C which is perpendicular to both A and B? And well, the answer is yes, we can. And how can we find it? Well, the equations we get by looking at A dot C equal to 0 and B dot C equal to 0, which is equivalent to them being perpendicular, give us these equations. And this is a really an underdetermined set of equations in that we have three unknowns and two equations. That's okay though. All we're concerned with is finding one solution. In fact, you can find one solution if we let C be this vector here, A2, B3 minus A3, B2, A3, B1 minus A1, B3, A1, B2 minus A2, B1, we get a solution. In fact, I would like you for question two to check that indeed if A is any vector and B is any vector with components A1, A2, A3, B1, B2, B3, then A dot C and B dot C are equal to 0, where C is this vector right here. So this vector right here we are going to define to be the cross product of A and B. We write it as A cross B, and it's this vector that we just wrote over here. Note, this is a vector. Unlike the dot product, this is in fact a vector. So that's kind of nice. I'm starting with two vectors, I multiply them, and I get another vector. All right, but this is a pretty annoying expression. Let's see if there's a nicer way to deal with this. So the formula for the cross product could be a little bit daunting. It could be hard to remember what exactly goes where. So a lot of people like to use sort of a notational convenience to help them compute it. We use something called determinants. If you're taking linear algebra now in the future, you will learn about determinants. They tell us something about the solubility of linear equations. When you have the same number of unknowns as you have equations, but it gets used a lot in geometry and in calculus because it also tells us something about the areas of certain shapes. It tells us something about, say, changes of variables. It tells us something about something called smoothness when it comes to looking at curves in space. It's really just a fantastic concept that gets used all over the place. And this may be the first place you're seeing it. So in the 2 by 2 case, a determinant looks like this. It's just A1 times B2 minus A2 times B1. Fairly simple to remember. This times this minus this times this. In the 3 by 3 case, it is immediately much more complex. However, determinants can be defined sort of iteratively, where the next case is defined in terms of the previous case. So we can evaluate the 3 by 3 determinant in terms of something called minors of 2 by 2s, 2 by 2 minor determinants. So what we do is this. We start with A1, and then we ignore the row and column and look at just the 2 by 2 determinant left, ignoring the first column and the first row. and we get A1 times the determinant of B2, B3, C2, C3. Then the signs will alternate. Now we subtract A2 times the determinant that's left when we get rid of the first row in the second column, which is B1, B3, C1, C3. Finally, we add A3 in the determinant that's left when we get rid of the first row in the last column. That should read, that's incorrect there, that should read B1, B2, C1, C2. All right, and then you can go ahead and evaluate these things, and you end up with a big thing that has 6 terms. Not the prettiest thing in the world, but whatever. So as an example, let's evaluate the 3 by 3 determinant, 1, 3, negative 2, 4, 5, 0, 2, 1, negative 3. And I'll do this out completely by hand to show you it's really not that crazy. So we take the first entry of the first row, which is 1, and we multiply it by the 2 by 2 determinant, excluding the first row in the first column, which is 5, 0, 1, negative 3. Now subtract the next entry in the first row and multiply that by the 2 by 2 determinant, ignoring the first row and the second column. We get 4, 0, 2, negative 3. And then finally I add the last entry in the top row, which is negative 2, times the 2 by 2 determinant you get by ignoring the first row, last column, which is 4, 5, 2, 1. Now this is 1 times, well, 1 times whatever is whatever. So I get 5 times negative 3 minus 1 times 0. That's my 2 by 2 determinant. Minus 3 times 4 times negative 3 plus, minus 0 times 2. Minus 2 times 4 times 1 minus 5 times 2. This works out to, that's negative 15, minus 0, great, minus 3 times negative 12, minus 2 times 4 minus 10 is negative 6, that's negative 15, plus 36, plus 12 is equal to, looks like that's 33. Great. So that is how we can evaluate a 3 by 3 determinant. The 2 by 2 determinant has a really sort of nice picture or diagrammatic sort of representation, which is this. We think of it as adding the product of this main diagonal here, and then subtracting the product of this off diagonal here. So down to the right, we multiply these guys, and they're positive. Down to the left, we subtract those guys. So it's like this nice sort of thing right there. A1, B2 minus A2, B1. That minus that. Great. For the 3 by 3 determinant, it's not so nice, but there is a nice sort of diagrammatic way that could be another nice way for you to try to evaluate this. If you might prefer this over the sort of iterative definition in terms of the 2 by 2 minor determinants. So it looks like this. What we do is we draw our 3 by 3 determinant, and then you copy the first 2 columns off to the right. Then we do the following. The 3 by 3 determinant will be the following. We take the product of this diagonal and add that to the product of this diagonal, and then add it to the product of this diagonal. So A1, B2, C3 plus A2, B3, C1 plus A3, B1, C2. And then we subtract the product of this backward diagonal, A3, B2, C1, and then subtract this backward diagonal, and subtract this backward diagonal, and put it all together. And if you multiply out this definition and the prior definition, you'll see you get the same exact formula. So either way works. So let's just try the previous example again, but doing it this way. So I'm going to copy down the first 2 diagonals, and then I'm going to start multiplying along these diagonals. So along this first one, we get negative 15. Along this second one, we get 0. Along this third one, we get negative 8. And yes, these are negative numbers, but, and I said they should be, we're adding them. It's not that they're positive numbers, it's just that we're taking them for what they are. Now going in the backward direction, we will be subtracting. So negative 2 times 5 times 2 is negative 20. So I'm going to make that positive 20. And then 1 times 0 times 1 is 0. And 3 times 4 times negative 3 gives me, that's 9 times 4, that's negative 36, but it's going to be positive. So that'll be positive 36. And then I put these guys together. 20 plus 36 is 56, minus 8 is 48, minus 15 is 33, which is exactly what we got last time. Good.